In this video, we'll be working with the work energy theorem, mechanical energy, and chemical energy. You can pause the video here and read the question. Assuming you have no idea how to start this question, let's break this into steps. First, the question is asking us about saving on gas if we reduce the weight of the car. Now, let's look at the section talking about engines converting chemical energy into mechanical energy. If engines are converting energy, this means they're doing work, so the work energy theorem should come to mind. Let's look at some key words. We have drag and friction, which are both non-conservative forces. At this point, you should also consider how they are doing work in this question. Let's review what we want to know from this question. We want to know the gas savings when we reduce the mass of the car. To do this, we need the number of liters consumed in both cases. To get this, we have to look at the amount of work the engine did. But before we start, we need to define our system, which is the car. The engine is not going to be part of the system because it does work to move the car. The force the engine exerts on the tires is internal, so we don't consider this. We're going to say that the work done by the engine of the car is the work of the ground. The force of the car, which is caused by the engine on the ground, and the force of the ground on the car are action-reaction forces. This is Newton's third law. For any problem, we need to first draw a free body diagram and define our forces. So here we have the direction of motion, the normal force, and the weight. We have friction, the drag force, and we have F ground, which is the propelling force by the ground. This is the propulsion force that the ground exerts on the tires. Before we continue, we need to make two assumptions. The first is that the car moves at a constant speed, and the second is that it's traveling on a horizontal surface. This will make things easier to calculate. So here's our work energy theorem. So in this equation, we have non-conservative forces and conservative forces. We actually don't have any conservative forces doing work, so we can set this to 0. A conservative force like gravity doesn't do work in this case because the car is on level ground. And based on our previous assumption about speed being constant, we can set delta k to 0. When we consider our non-conservative forces, this is what we have. Remember we said friction and drag are non-conservative forces, but we didn't specify which friction it was, which is now going to be our task. The correct answer is rolling friction. Let's see why. The flattening of the tire due to its contact with the ground causes rolling friction. It slows down the car, so it's opposite the direction of motion. In case you're wondering about the other friction, kinetic friction and rolling friction don't act at the same time. And the propulsion force the ground exerts on the tire is already a type of static friction. So we will be solving for the rolling friction. Going back to the question, we have the work of drag plus the work of the rolling friction plus the work of the propelling force of the ground equaling 0. Recall the definition of work, which is W equals F, the force, D, the magnitude of displacement, and cosine theta, the angle between them. After we solve for the work of the drag and the friction force, we get negative drag work and negative friction work. We can plug that back into our non-conservative force work equation. When we solve for W ground, this is our final equation.